Section 10.3, which could just be considered 10.2 extended, is displaying data part 2. We're going to look at a few more graphs and ways of displaying data. The first one we're going to look at is something called a line graph. A line graph is line segments that connect one dot to the next, typically showing a trend of a variable over time. And you should think about it as being something like connect the dots. Right? You've all been to the restaurants that give the kids the pieces of paper and they connect the dots, right? That's what this kind of a graph is. It's connect the dots. Okay? So there are data that it makes sense to display this way. There's data you've seen in graphical sense, like in media, that's displayed this way. Can anyone think about or think of an example where you've seen connect the dots for data over time in media?
Like graphs and where they're like this.
Mm-hmm.
I've seen sometimes like when in debates, like in presidential debates, something like that, sometimes they'll show like what the audience reaction is when someone says something.
Yeah.
Kind of go up or go down depending on what the person says in the debate.
That's a good example. Yeah.
Like TV show ratings.
Yep. Ratings for TV shows. Yeah.
I did something like, I've seen it where it's like the use of Facebook has gone up or down, and how they've shown it like throughout years, how it's gone up or down, and different things like that.
Yep.
And even like different social media, like Facebook went up when MySpace went down.
Yep. Yeah, so they're using, and they use line graphs a lot for these things. If you look at enrollment trends of OBU, every fall or something, they'll look at the last few years, and they might display it in this way as well. Another one that I know you guys have probably seen, maybe you haven't paid much attention to it, but it's displayed like this very clearly, is the stock market. The stock market trends, and you see lots of crazy things, kind of like Leah was doing in this area, like this. It does like that, right? That's what it does, yeah. Okay, so some data makes sense this way and some doesn't. A lot of data can be drawn in this way, even if it isn't maybe the most natural way to think about it. But this is always the change in something over time. Okay, it doesn't make sense to connect line graphs together if you're measuring responses for, like the letter grade stuff we did. It wouldn't make any sense to graph a dot at each one of those points and connect those dots. That doesn't make any sense. Now, if you looked at a student's grade performance over time, that'd be okay. But this doesn't make sense in terms of a grade disbursement or something like that to do, okay? We're going to do an example. A learning specialist tracked the average reported studying times of her students. We're going to create a line graph for the data that she tracked. I can't remember. I think I just flipped it to the end last time I taught this one. I probably should put it in the middle here, but okay. So we have Monday through Sunday, and these are the amount of it is the amount of time a student spent studying each night. So it says on Monday we have 1.5 hours, Tuesday 1.75 hours, and so on. And I'm going to pull up this graph at the end. So what we're going to do is we're going to draw an XY axis, horizontal vertical axis, and we're going to put, in this case, it's the days of the week as the horizontal axis. Time, as we do these, is always going to be on the horizontal axis, the x-axis. So in this case, we're doing the days of the week. So I'll space them out evenly, of course, just like we talked about last time. So here's Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. This is a fixed week, right? A fixed in time kind of week. If we were looking the change of time over years, we do have to be a little bit careful of where we start our years. And when we encounter one of those, I'll show you what I mean by that. But the fact that this is the days of the week and we're sort of just looking at one glimpse of a week in time makes things a little bit easier on this problem. Now, the vertical axis is our hours spent studying. So you have the data. I'm not going to flip back to it on the screen. But what is the smallest value on the data that you have listed? 0.25 hours. And if you notice, all of these are in increments of 0.25, right? So I'm going to make my vertical axis 0.25 apart. So this is 0.5. This one's is 1, sorry, or 1.0. Then I have 1.5. And I have 2.0, or just 2. And then I have 2.5, but that's further than I need to go, isn't it? I think so. We have axes, which means we need to label them. Our horizontal axis, what is that? It's days of the week. And I don't know that I necessarily have to say this, but I'm going to mention it just in case anybody thought that it didn't matter. It does matter that they go in order, right? Monday, then Tuesday, then Wednesday. So we do need to go from left to right in some kind of an ordering. And then on the vertical axis, what are these numbers representing? Yeah, this is hours studying. Or you could say time spent studying in hours, something like that. The fact that it's measuring it in hours needs to be there in some fashion. And the fact that it is studying times matters and needs to be there. The next thing we're going to do is we're going to plot the points. Okay? So the first one says Monday is at 1.5 hours. So that's right here on my graph. The second one is Tuesday is at 1.75 hours. It should be right here. Wednesday is at 0.75 hours. It's got to be because they went to church, right? It is in my household. Spending times go way down on Wednesday. Thursday is 2 hours. Now, truth be told, somebody said that on Friday they spent 0.25 hours studying, and I think they're probably lying. I don't know very many kids who study on Fridays, do you? You guys don't even do that, do you?
Depends on how much homework.
Yeah, I have a lot.
Okay. But you're also talking about college students. I don't think this is the average high school student probably here. Saturday is 0.25. And then Sunday, apparently they need to get some homework done before they go back to school. And so they're back to 1.5 on Sunday. Now, if we stopped right here, this data without any lines drawn would be what's called a scatter plot. Okay? We're gonna hit scatter plot here in a second. I'm gonna draw you another scatter plot as well. But I just want to make mention of the fact that if I don't put any lines here, I actually have a graph called scatter plot. Okay? But we're doing a line graph right now, which means that we're going to connect the dots in order. And as with any connect the dots, the in order matters. Otherwise, the picture doesn't look right when you're done. So we're going to connect the dots in order. And the point is that it's supposed to show the trend in the data over time. Now, the more time you have, the better you can see trends, things like that. There's one more thing that I need on this. What is it? I need a title. What would be the title for this?
Hours during or
Can I use time because I already put hours on there once?
time studying during the week.
Yeah, time studying
Or per week or something.
during a week or per week or something like that, yeah. Easy enough? Okay. Now we're going to talk a little bit more about scatter plot. I've already mentioned a little bit about it, but let's go back and pick up the rest of the information about that. A scatter plot is often used when a relationship between variables cannot be easily depicted even by a broken line. Now, we could depict that last one by a broken line. We could do it without a line and call it a scatter plot as well. But the next set of data you're going to see is a little bit more complicated. And the reason it's more complicated is because we have multiple x's and multiple y's going on. Okay? So this says Coach Lewis kept track of the vertical jump heights of his starters. The vertical jump heights his starters were able to jump over 8 years. So he has the 5 starters on his basketball team, okay? Vertical jump height means how much you can jump straight up and down, okay? Not like long jump, like vertical jump. And these are, and this should say in here, and I left it off last semester, apparently I never got it fixed, jump heights in inches. That should actually have been written in there. I'm not just making that up, okay? In inches. I don't even think it's inches. I think it's centimeters now that I'm putting there because I don't think those values make sense in inches. We'll go with centimeters because I think that's more realistic with what we've got going on. Okay. 65 inches would be a lot. Yes, ma'am.
Our notes say it was over 7 years.
Okay. How many do I have here?
I don't think.
Okay. There are 7. So this is also a typo. Thank you. I'll I'll fix the typos. Next semester, there will be fewer typos. This semester, there's fewer than last. It's a fun thing. Okay. All right, so we've got all of this data, and we're going to put all of this data on a graph. And what we're going to do is we're going to end up with lots and lots of data because there's lots of data in this graph, right? Okay, so draw yourself, sketch yourself some kind of a axis. And I need these years. So this is the first time where I'm talking about the fact that this is a little awkward. I'm starting in the year 2002, but this is just when he's keeping track. It doesn't mean that time did not exist before then, right? We're not really looking at this kind of like we were looking at the last example. So we have to do something that's a little bit weird. So what we have to do is at the very beginning of this graph, we need to indicate that this graph has a break in time. It doesn't start at year 0. Okay, it's a little awkward to do this, but what we do to do that is we actually draw this sort of deviated line. And then we continue our line after this. Draw a break like that. Okay? And then we can start with the year that we want to start with. So this is the year 2002. And I am going to put in just the last digit of them to save myself a little bit of writing. So this is 2, 3, and so on, up to 8. My grid's a little small, so I'm skipping every other one just for spacing. And then my vertical jump heights, notice, they also don't start anywhere near the number 0. And the horizontal axis usually means 0, right? But I also don't want it to be like 0 and then have this big old gap where there's nothing showing up on my graph. Are you guys with me? So I'm going to do that same sort of break right over here that I just did a minute ago. So this break indicates that I'm actually not starting the axis in the right location, kind of. So let's actually see what my values are. What's my smallest value on this particular set of data?
60.
There's one smaller. There's a 58. What's the biggest value? 77. So 58 is in the bottom left-hand corner, 77 is the top right-hand corner. So we need from 58 to 77. I'll count by 2s so that I make sure that I actually have enough space here. So this one would be 58, 60, 62, 64. I'm not sure if I'm going to have enough space. We'll see. I may have to rethink this. 66, 68, 70, 72. I'm close, so you just watch what I can do. So you can't do that on your paper, can you? Okay.
Would they be able to label every 2?
Yep, that's what I did. Yeah, I was labeled every 2. It just needs to be something that's clear enough, you know, that you can look back at it and know what those numbers were. And I can look at it and know which numbers were. All right, so we have numbers labeled. Let's actually describe what the axes are. So the bottom axis is maybe the weirdest one because I changed 2002 to 2. And I need to label that somehow that I did that. Does that make sense? So the easiest way to label that is to say that this is the number of years after what? The number of years after 2000. That's the easiest way to describe that. There are other things you could say that would be okay, but this is the easiest to say, years after 2000. What about my vertical axis? What in the world are these values over here on the left?
Heights in centimeters, heights jumped in centimeters.
Okay, so these are the vertical jump heights.
Can you put it in centimeters?
Definitely. So somewhere over there needs to mark that these are measured in centimeters. And then we're going to put data in. So we're going to take our 2002 data and we're just going to put a dot for every single one of them. So I have 65, 63. So above 2002, I have 65, 63, 60, 62, and 58. In 2003, I have 67, 65, 66, I skipped the 64, sorry, 67, 65, 64, 66, and 62. In 2004, I had 67, 68. '66, '65, '64. 2005, 68, 70. '67, '66, '65. In '06, I had 70, 68, 67. 69 and 66. And in 2007, I had 74, 72, 73. '70 and 69. And then in '08, I had 77, 75. They got tall, huh? I got jumping tall. 77, 75, 72, 71, and 70. Okay, so the point of a scatter plot, when a scatter plot seems most appropriate, is that while it's not really a lot of sense made to draw a line to connect all these dots, I mean, that would be weird, right? There is some sort of sense of what the data is overall doing, right? You can look at it and you can say, overall, it's increasing. Agreed? And that's the kind of thing that we're looking at when we're looking at the data for these. Now, there are two things we still need to do. The first one is to make a title for this. So what is the title for this graph?
Height of jumpers over 7 years.
You see, these are jump heights. You can put the centimeters here if you'd like. It is on your x-axis or our y-axis, so if you don't put it here, it's okay. So vertical jump heights over 7 years. You could say from 2002 to 2008, some version of that. These are the heights. You could put the word vertical in there, but again, we put the word vertical on our vertical axis, so we don't have to put it there necessarily. There's one other thing that it asked us to do right above this sort of space where your graph is. It says, what kind of association is there for the data? You guys see that? This data, what kind of association is it? Well, the question's actually asking you, over time, what's happening? As the x values increase, what are the y values doing? They're increasing. So we call that a positive association. You can kind of think about the word association as related to the idea of slope. What is the slope doing if I were to graph some sort of a line that was sort of mimicking what's happening here? Well, the slope is going up, you know, right? So the graph is going up, so the slope is positive, so we call that a positive association. Positive association. Last question, or the last thing here is called a trend line. A trend line is a line that closely fits the data and can be used to describe it. This is often called a best fit line. Have you heard of line of best fit before? Or trend line before? They are used quite frequently, and they can be used to fit pretty much any kind of data. What they do is they mirror what's going on. The attempt is not to hit any of the particular data points at all. It's just to show the trend of the data over time. So what we're going to do is we're going to do the same data that we had before. I'm not going to have you redraw something. But what we're going to do is we're going to draw the trend line on top of the scatter plot. Now I'm going to warn you right now that whenever I ask questions about this in your test, people confuse the trend line with the scatter plot. So make sure that if I ask you to draw the scatter plot, you don't draw a trend line. If I ask you to draw a trend line, you don't draw a line connecting everything, right? These are all three separate concepts. Be able to clearly identify which one is describing what. So we're going to take the scatter plot and we're going to draw a trend line for it. And again, our goal is not to hit any of the data points, though we likely will hit some of them. It's just to give the overall picture of the data over time. So you're sort of trying to balance. When you draw the trend line, you're trying to draw the trend line that looks most closely related to the slope of what's going on. And it kind of balances the points on either side. Okay? We're not trying to do this in a super precise and exact way, although you definitely can do that inside of statistics and calculus courses. That's not the point. The point is to give an overall picture of what's going on and approximate. So when you draw your line, it may not match exactly what my line is, and that's okay. But your line probably will look something, I don't know, like that. Does that seem reasonable? Or maybe you feel like, okay, I'm a little too far away from that top point. Maybe it's got a little bit more of a slope going on than it, like that. So whatever you think it is, draw your best approximate guess. Now, just because there's multiple things that could be right doesn't mean that there's things that could also not be wrong. You could definitely draw this and be wrong, okay? It has to fit the overall pattern of the data and what's going on. Now, when you get to your group work and your homework, it's going to give you like a scatter plot like this, okay? And it's going to ask you to draw the trend line on there. I don't expect that you're going to copy down all the little dots. But because you're using notebook paper that's a little bit see-through, you can place your paper on top of the graph, draw the edges of the graph, and then draw your trend line on there. And I could do the same thing. Then I could take your paper and put it back onto the line, the data itself, and I could be like, yeah, it's fitting it pretty well. You guys with me on that? Okay. So this is the trend line. A couple things that are a little bit weird, I should make mention of actually over here, is that what we're going to do is it's going to ask us to create an equation for this line. Okay? So equations have slope, yeah? And they have y-intercepts, or an ordered pair on the data set, or something like that. So it's a little bit weird because our horizontal axis is not exactly x equals 0, right? We did this weird little jutty up thing going on here. It was strange, okay? So we're going to have to sort of make amends for that in a minute. But let's look for a slope of overall what's going on. You have to make sure that you're using the line, not the green dots that I have all over my screen, okay? So what I look for is I usually look for locations where I can easily identify an x and a y value for that particular point. So you may not have the same ones that I do, but like this one right here looks fantastic. I'm crossing right through that green dot. So I'm going to use that one on my graph. You need to look for ones on yours that are kind of like that. The other one down here that looks at least pretty darn close is this one.
So pick your two just closest ones to the line.
Yeah, and it doesn't even have to be those particular points. Like for instance, let's say, in fact, I like this one really well. Look how nice that point is right there. There's no green dot there, but it really crosses very nicely at one of the corners, if you will. So you could use that one if you wanted to. I'm not going to use that one because that one would be using a value that's in, it's going to be decimals. I don't really want to use the decimals if I don't have to. But that one would work okay. So it doesn't have to actually be one where you have a data point. Just one that it looks like you're pretty sure that this is x equals this and y equals that, whatever those are. So I'll go back and I'm going to use this one just because it was a pretty nice value. Okay, so let me write down ordered pairs for what I have. This one was 872. And this one over here was 262. And I'm going to find slope for those two values. So how do you find slope? Y'all remember?
Rise over run.
Rise over run. So it's the change in y, like y2 minus y1, over x2 minus x1. Okay. I don't care which one you call x1, y1, which one's x2, y2, but you do need to go in the same order. So if you decide that this is x2, then this one's the y2. They have to go together. And that means then that this one would be x1 and this one may be y1. So y2 would be 72 minus y1 is 62. For me, yours may not match this. So please make yours match your data. And then x2 on mine is 8 and x1 is 2. So I'm getting something like 10 over 4, which would be 5 halves, or 2.5. I don't mean 4. Why did I write 4? Let's try that again. 10 over 6. That looks better, which would be 5 over 3. There we go. So a little bit more than 2. right? That's what I'm getting. When I did this on my paper, I actually got an exact 2. The values that I did when I did my paper version of this says my slope is actually equal to 2. Okay? So now, if you give me an answer where your slope is like 3.5, that would be wrong. I mean, that's not going to be close, right? But if your slope is somewhere close to the value 2, like 1.5 to 2.5, something like that, or if I can see that, that's okay. Okay, so that's the slope approximation that I'm getting. So this is M. Now, you mentioned, I think, Hannah, the slope formula where you had the slope-intercept form of a line, like y equal mx plus b. This equation is a good equation for us to sort of plug M into. But it only works if I know what b equals. And we talked about the fact that it sort of looks like it should be the vertical axis, this point right here. The problem is, what year is that? Well, it's not the year that I'm sort of marking as 0, because that would be 2, and that would be 2 years before this. It would actually be right here. So you have to be a little bit careful. So wherever it is that you've decided, in this case, I called my x-axis years after 2000, then the 0 would be my intercept that I'm looking for. So like if this is 3 and 2, then this would be 1 right here, and this -1 over here is actually where 0 would be. That's awkward. So I have another fix for what you can do instead of having to think about your graph to make that happen. You can use any one of those values that you just circled, 872 or 262. Okay, so pick which one you want to use. I'm going to use the 262. So I have y equal mx plus b. I know that my m was 5/3. And I'm going to use an ordered pair x, y. Doesn't matter which one I pick, but it's one of the two that I use to find slope. So I'm going to do the 62, which was the y value, and the 2 was the x value. And I can use this to solve for the b value that would correspond to the year 2000, the y-intercept. Did I put it in the right spot?
The denominator is 2 and it should be 3.
Oh, I changed it, didn't I? Thank you. I was just hopeful thinking to turn anything into whole numbers, I think. All right, so I have 62 here equals 10/3 here plus b. And I'm going to have 62 minus the 10/3 equals my value for b then. Obviously, whole numbers are easier to work with on this one. 10/3 would be like 3 1/3. So if I had 62 minus 3, that would be 59. And then I need one more third taken away, so it would be 58 2/3. You certainly can use a mixed number or a whole or a decimal. Decimals are fine as long as you're not approximating. I want an exact value for whatever points you have. We need the equation of the line, though. So the equation of the line is y equals m, which was 5/3 x, plus b, which I just got awkwardly in mixed number form, was 58 2/3. Somewhere, somehow, you have to indicate that this was years after 2000. X equals 0 is the year 2000 here. X equals 2 is the year 2002. Because if I need to evaluate this in the year 2012, and I don't know that x equals 0 is actually the year 2000, I might inadvertently put in 2012 for x when I should have put in 12. You guys with me? So this is measuring the centimeters of a jump. Centimeters is sufficient, but it's of a jump specifically if you would like. The important part, the most important part, is to say where x equals the years after 2000. Otherwise, using this equation for anything is not possible without that information. So this is part B, I think, on the problem that we had before. And there's a note even in your notes that says something about this fact. This must contain appropriate supporting language to allow the equation to have meaning. You can't use it if you don't put x as years after 2000. You can't use it. So then, using the equation, what would you predict the jumping height would be this year? So what year is this? 2016. So the 2016 would mean that I'm going to let x equal what? 16. And that's what I'm going to use in my equation. So my equation was 5/3 x, so that's 16, plus 58 2/3. I don't have this written down for the year 2016 because the last time I taught the class it was 2015. And my equation's slightly different, right? Because I already told you that my slope was slightly different. So you guys are going to have to work with me. Help me out here. What is 5/3 times 16 plus 58 and 2/3? What am I going to get? Do you have a value, Abby?
No.
Okay, sorry, just checking. 80 over 3 plus
116 over 3.
Okay. 80 plus 116 would be 196 over 3. What does that give us in terms of whole number and partial? Mixed number form. Better be more than 58. It's already started there. 196 divided by 3. What is the whole number part?
65.
65? And it was 0.3 repeating? 3 repeating is what fraction? 1/3. Thank you. So this is 65 and 1/3. What? Centimeters.
So did ours have to be similar to your answer?
It will depend on your data. I mean, they shouldn't be drastically different. But this does not sound right. I'm feeling like that we've got a wrong answer somewhere because this answer doesn't make sense to me. Are we sure that 16 times 5, that all those values are correct? The answer I got the last time I did this for 2015 was roughly 90 inches. 90. Well, you can only do it in decimals if you're not going to deal with the fraction that's the third and I mean, like you can put the 3 repeating, but your final answer shouldn't really have repeating decimal notation. That's not really mathematically very friendly. Was it my fraction? Hang on.
Oh, 80 times 116 is 1/8. No, never mind, I did that wrong.
I'm going to see. I got a slope here before that was closer to 2 than I have now, so it is going to be lower than my value before.
That mixed number, like the 58 and 2/3, should be 176 over 3, not.
Did we have that written wrong?
85.3.
From here?
Yeah, 85.3 repeating.
So, I'm sorry, I'm on a different screen. Back here is the one you're talking about. The 58 and 2/3
That should
is
be
176. That would be better. Okay. All right, and then 176 plus the 80 is 256. Divided by 3 is 85 and 1/3. I have 0.3 repeating, so 85 and 1/3.
So my one is 85.5. Or
Oh, you're close. Yeah.
89.5. That's
Yeah.
close.
Yeah, absolutely. My answer, like I told, my answer from last semester was 90. We're in the same ballpark. All right, tiny little bit more. Association. I told you that there was a relationship between association and slope. So without saying anything to a neighbor, I want you to write down what kind of association you believe A, B, and C represent as equations of lines. We're going to check and make sure you're right. So just write down what you think. I told you before. What kind of association?
It's like weird stuff on our.
I don't know how just write down what's on here. I don't know how the gobbledygook happens sometimes. It doesn't even make any sense. These are PDFs. That's why I save them that way. So I don't know how that's even possible. It's weird.
It's funny because mine's like yours.
Yeah. And it never happens consistently across the board to everybody's. Their equations didn't show up right on their pages when they printed them out, so it's a problem. What did you guys write on the first one? What kind of association is it? It's negative. The slope is negative, so it's a negative association. How about the second one, B? That is a positive association. What about on C? Yeah, there's zero slope, right? There is a slope. The slope is 0. So what we say is that there is no association because the slope is 0. Basically, if you were to draw a line, it would be horizontal, which means that there is no change over time. Right? There is no increase or no decrease over time. No association.